All right, here we go. Thanks for reminding me, Marty. All right, so welcome to the first ever virtual meeting for the astronomy section at Rochester Academy of Science. For those of you who don't know me, my name is Mark Minerich. I'm your president, and I'm pleasantly surprised, not surprised, but pleased that we can do this way. So I'm glad that those of you who are here, they're able to join us. We've got people from all over the country here. I know that there's somebody here from Albany. Hey, Val. My brother's here from Arizona, and I think that Rick Albrecht was going to try to come in from Georgia. Yeah, he's in. Looks like he's in here too. So by doing it this way, we actually cover the whole country. So it's kind of cool that we're all together like this. Very cool. All right, so for today, I want to first thank Dave Pesch and his company, Expudo, for donating this service, the big blue button. So Dave's up there. He's the second person up on the video there. So thanks, Dave. Appreciate it very much. This is fantastic that we're able to do this tonight. So I've got everybody muted. Chat is available to anyone that's on. So I would advise you use chat if you want to communicate with me. Let me know that I'm missing something or something's going on. Or when Dr. Richmond starts his talk, if you want to have a question, if you text it, then I can give him the interruption to ask that question when he talks while he's giving the presentation, so that we're not talking all over each other. So chat me. You can use the general chat, but if you chat me directly, then I know that I'll see it if other chats going on in there. And then I'll unmute everybody at the end of the presentation, and we can if you have a headset, or that's probably the easiest way to talk, because you do get a little echoey. That's why I'm wearing headset, so I'm not quite as echoey as I would be otherwise. All right. So here's our agenda for tonight. I want to welcome everybody here. We've got some announcements. If we need it, we'll take a break, and then we'll have a feature talk by Michael Richmond on cutting the Hubble constant down to size. So look forward to that. All right. So I will unmute you for a second here. Did anybody get to do any observing? I know we've had some real nice weather. Has anybody been able to do any observing? You don't have to all speak at once. I know a bunch of people saw Venus and the moon. Well, did I unmute you? Let me see. You could unmute yourself. Go ahead.
About observing, last night I saw Venus going beneath the Pleiades. It was crystal clear in Honey Falls, and it was beautiful. Did anybody else see that?
I saw people's pictures of it.
Oh, wow, I'm surprised. It was really nice.
Yeah, I was out. I took a look at it at night.
Yeah, been watching Venus get closer and closer to the Pleiades over the last few nights. It's pretty interesting. It's going to go past it tonight, or it's going to be
Speaking
past
of astronomy, we were making custom astronomy masks that's got the DNA and astronomy on it for medical
cool.
mask with the metal insert for the nose, and these are high tech. But we distributed a bunch of these. It's got adjustable bands. Everything's replaceable. You can run it in the washing machine.
Excellent.
Great.
Did we get any other observing in? No. Okay. Well, I wanted to remind people that there's still a chance to renew your membership for 2020. I know with all that's going on, it may have been maybe less on your mind now, and certainly can understand that. But I wanted to show you at the same time that your keys are due. But I wanted to show you a way on the next slide here to renew via PayPal. When I finish today's presentation, I'm going to send a PDF to Peter Bono. Peter, if you could put this up on our website, then people have the notes from tonight's meeting, and you'll also have these instructions to pay via PayPal if you're interested in doing it that way. This way, no money needs to change hands or checks. Bob doesn't have to expose himself to handling a check, or you don't have to expose yourself to Bob or Bill or anybody else. It's a nice, clean way to deal with renewing your membership going forward. More information on that is all in there on how to do it. The instructions are there. I'm not going to do it blow by blow, but this will be on a PDF on the site if you want to follow these steps to do it this way. It's actually pretty simple, but you do need a PayPal account to do it this way.
Okay, I'll get it up there.
Excellent. Thanks, Peter. An announcement that the Blackfriars Theater Group has canceled the next two productions, so they're canceled through June, and they've determined the thing to do is to cancel these, and what they're going to try to do is reschedule Silent Sky, and the show that was going to be done after that is Calendar Girls for September. And if you want your money back, or you want to just donate your money to Blackfriars, let them know. If you've done business with them, you've probably gotten an email from them on what to do. But if you were interested in doing this, Silent Sky was a play that Blackfriars had invited us to, and we were going to do some consulting on. But as it turns out, this whole thing got pushed out till the end of the summer, beginning of the fall. So I want to make that announcement. So hopefully we can see this come this fall. Something we can do is the Northeast Astronomy Forum is going to be virtual now, and they're actually going to have the event this in September 12th and 13th, that weekend. I'm not sure exactly the dates, but the Saturday, Sunday in September, the Northeast Astronomy Forum will be doing the regular get-together. But there is a virtual experience where the talks will be streamed. They always have been streamed, but their talks will be streamed, and vendors will also be doing some videos as well. If you go to the NEAP site, just type in NEAP in your browser, and it will direct you to NEAP, and you can actually see the virtual experience there. In the past, they've always streamed stuff that was going on there, but it looks like they're going to do all the speakers. I don't have the list of speakers. If you go on their site, they only list the first speaker of the day, which is just the introduction and the welcome. And then the first in another area is a telescope demonstration. So go to the site, take a look. It's something to do if you had planned on going to NEAP. If you've never been there, you can actually experience what some of the vendors do there. It's kind of a cool experience if you've never been to NEAP, the Northeast Astronomy Forum. I put on there you may need to register, because earlier in the week I wasn't sure if you actually had to register in order to get the virtual experience. But I know in the past they've always streamed their event. You could actually go online, actually see people wandering around through all the booths, and you could watch some of the talks as well. The talks are pretty interesting. They get some pretty high-profile speakers, but I've not seen who their speakers are this year. Another thing that you could do is there are other live stream events. The American Astronomical Society has a whole list of stuff that's going on. This is a really long link, and I don't think you need to be a member to get to this link. That's another reason I will post this. But if you go to their site, they do have other live streaming events that are happening all month long, next month long. They even have dates that go into the summer and the fall. But if you go to their site, I just uploaded a piece of the Excel spreadsheet that actually had the talks, the dates, and links to the YouTube or Zoom or whatever they're being hooked up to. There's all kinds of interesting talks that the American Astronomical Society is doing. And I want to thank Valerie Rapson. I think you put that up on your Facebook page or something earlier in the week, but I took that from your page. I said, well, check this out. And it turns out there's a whole bunch of cool stuff to attend at the courtesy of the American Astronomical Society. One more thing to do. For upcoming events, really, it's hard for us to know what we're going to do. Obviously, anything in April is canceled. Our meeting is actually scheduled for Friday, May 1st, but who knows? It's doubtful that that's going to happen. What we'll do is we'll ask Richard O'Shaughnessy if he wants to possibly use this forum again. Maybe we'll do this again in May for our meeting. If David will let us do that. Excellent. Thanks, Dave. But yeah, pending an improvement on the current large gathering status, we're probably not having that meeting in May. So we'll try to do something like this again in May. And then any other near-term events, I'll let the group know by our newsletter or by the email group. If you're not in the email group and you got this from me, shoot me a note. I'll help you get into the email group. All right, that's it for my announcement. So it's probably not enough time to us to anybody really need a break. So what I'll do is I'll introduce Dr. Michael Richmond, a professor of physics and astronomy at RIT. And what I can do is we'll find Michael in this list of people here. I'm going to make him a presenter. You there, Mike?
I am here.
All right, I'm going to promote you to make you the presenter so you can share your presentation.
Okay.
All right, and it's all yours, Dr. Michael Richmond.
So I'm not sure if my voice comes through clearly. I hope someone will give me feedback. Either I won't be able to see anything in the chat windows. You can chat things, but Mark will have to act as moderator. If something's wrong with my voice, please tell him in the chat and I'll try to fix it.
All right, I can hear you fine.
All right, so whoops. What I'd like to talk about today, what I'd like to talk about tonight is a little bit of history. You probably all know something about the Hubble Constant. It has something to do with
We can't hear you, Michael. Mike?
now I'm unmuted, sorry.
Okay,
Can you hear me at this point?
now we can hear you.
All right, I'm wondering if the big blue button is muting me on purpose, but am I still audible?
You're still audible.
Okay, so history. What I want to talk about is what is the Hubble constant and why has its value decreased by roughly a factor of 10 since it was first determined back in 1929. If you have questions along the way, please indicate to Mark using the chat function that you have a question, and he'll stop me and give you a chance to ask your question, and then I'll try to answer it. As I mentioned before, I can't see the chat window while I'm doing this, so I don't know that you have a question. I'll try to pause every now and then. And for those of you who want to challenge, you can get out your calculators and your pencil and paper at home. There will be a couple of places below where I'll ask if you want to try to calculate something in a sort of a quick and dirty way. And so if you want to play along, feel free to do so. There will also be one galaxy for people to try to identify simply based upon its picture. So if you want to get your favorite NGC catalog at the handy, do that as well. All right, so let me begin. Oh, by saying, if you find this stuff interesting, all of the material is available on a web page out of my server at RIT, and I'd be happy to give Mark the URL so that you all can copy it down if you feel interested. I'll ask him to send it out to everyone after the talk is over. So if I go past things too quickly, or if you just want to look at it later, the material's all there. You'll be able to look at it at your leisure.
All right, Mike, you want to put your presentation up?
Oh, am I not putting my presentation up? Sorry.
Put it up.
All right, hold on.
Share your desktop, maybe.
Yes, that's what I'm doing. I'm trying to. No. I want to start sharing my screen. Yes, share my screen. No, share my screen. Yes. Why is it not allowing me to share the screen? Allow. There. No, you're not seeing my screen, are you?
Not yet.
All right, let's see. I know we did this earlier.
Yes. So the blue plus sign at the bottom.
Yeah. I'm telling my computer to allow me to share it, and it's It's saying, no, I won't let you share that. I'll try sharing only this. An error occurred in screen sharing. Please try again. Awesome. Maybe what we'll have to do, Mark, is you'll have to share the screen for me if I can't do it.
Okay.
Let me try one more time. I can't share. So, Mark, let me give you the URL. Can you open a browser window on your computer and share that?
Yes.
Okay, go ahead.
Okay, why don't you give me the URL and I'll share the.
spiff.rit.edu/richmond/ASRAS. That should do it.
Okay. Okay, I'm there.
Just hit return. Scroll down to the very bottom.
April 3rd.
Yeah.
Okay. All right, let me do this. Copy this. Back over here. I'm going to take over control from you. And I'm going to, I think I can do this. Orbit.
Hey, Mark, what you might be able to do is to upload the presentation. So either make a PDF of it or just do the PPT itself. That way, Mike can take over control and actually move through the presentation.
It's not a PowerPoint. It's a web page. I guess I could generate PDF from it if you like.
Oh, okay.
But is it true that you can't
no, I can't
open it in your browser, Mark?
Let me see if I could. You know what? I can do this, and then what I could do is I could share my desktop. Let's see. I think I could share my desktop. How does that work?
I don't see it.
Hang on. Hang on.
There's one other thing we can try after this, Mark, if it's not working.
Okay. Can you guys see it now?
No.
Let me share my screen. There. How's that?
No, we still see your PowerPoint. Can you
How
close?
about now? How about that?
I still see your PowerPoint.
No.
Do other people also?
Let me try one thing. I'm actually going to bump some webcams off.
Okay.
See if that's causing a bottleneck. So try that, Mark.
Let's try this. Try this. How's that?
Something is
There we
changing.
How's that? There we go.
That's good.
Now you just got to tell me when you need to move it up and down. So
Righto. So, could you please increase the size of the font a bit? There might like zoom in other words.
Yeah.
Yeah. Oh, good. That's good. Okay. So, sorry for the technical delays. That's fine. What I'd like to do is talk about what is the Hubble constant, how do we measure it, why has its value shrunk by a factor of 8 or 9 or 10. So, to begin, what is the Hubble constant? So, I think I'm going to skip this. The next item was supposed to be a thing, an animation that would run on the screen. Given how things have been going, I'm going to skip that. Let's scroll down.
okay. All right.
Yeah, there we go. All right, let's talk about these guys. So, galaxies were determined to be other collections of stars, billions and billions of stars, far outside our own Milky Way, only in the 1920s. And one of the prime movers in that discovery was a man named Edwin Hubble. You see him there on the left. He was lucky enough to have access to some of the biggest telescopes in the world at the time, which were the 60-inch and the 100-inch reflectors on Mount Wilson in California. He and a few other astronomers used those telescopes to take the best pictures and the best spectra of galaxies. Shown on the right is a fellow named Milton Humason, who's not nearly as famous as Hubble, but who did a lot of the work. What we're going to talk about today is the relationship between the distance to a galaxy and the speed with which it's running away from us. Mr. Hubble, over on the left, he was sort of in charge of measuring distances, and we'll talk a lot about what he did. Humason and a few other astronomers were in charge of measuring the velocities. And even though Mr. Hubble is way more famous these days, as you're going to see, the measurements that he made have been modified quite a bit, but the ones that Humason made have pretty much stood the test of time. So, distance, velocity. What Hubble was the first to notice is that there seems to be a connection between these two quantities. Can you scroll down there a bit? Right. So it wasn't an easy thing to do. This little clip here in words, shown in italics, is taken from a paper published by Humason. You will notice that he took, to get the measurement, to measure the velocity of just one galaxy, and it's one of the nearest galaxies to us, he had to use his 100-inch telescope, biggest in the world, and take exposures of 33 hours, that's what the H is for, and 45 hours to get 2 spectrographs. Now, I'd like to ask those of you who are listening at home, how long is a typical night? You can type your answers into the chat window there. How many hours are there in a good astronomical night? I'm guessing the answers are rolling in. I can't see them.
I'm getting 12 hours, 6 hours, 8 hours.
Right. Are there any nights that last for 45 hours? And the answer is no. In order to make these measurements, and you can see, if you scroll down just a tad, you can see 1 or 2 examples of the spectra he took. What Humason would do is he would point the telescope at a target, get it all focused and set up, open the shutter, wait 4 or 5 or 6 hours, however long the night was, close the shutter, and then he'd wait for the next clear night. And when the next clear night occurred, he'd go back up, get everything pointed just right, hope that it was that the camera and the spectra and the film were all still lined up, and then he'd open the shutter a second time. And he would do that for 5 or 6 or 7 nights in a row before he exposed the film. So it was a real hard slog to make the measurements that he did. So let's scroll down and look at some of the results. So there's a graph, 2D graph, that you'll see if you keep scrolling down. Yep, there we go. You might need to zoom out just once or twice so that the whole thing will fit on the screen. And we can see the X and the Y. Yeah, so we can see the X and the Y axes. So on this graph, on the horizontal axis is the distance to a galaxy in units of megaparsecs. And on the vertical axis is the speed with which it is moving. Positive means going away from the Earth, and negative means coming towards the Earth. So in 1929, Hubble took these measurements of positions and velocities, and he noted that there was a pretty simple connection, that if you looked at a distant galaxy over on the right, it was probably moving at a very high speed. If you looked at a local galaxy close to us over on the left-hand side, it was probably moving with a pretty low speed. If you scroll down to the next picture, you'll see that Hubble was able to do what scientists love to do, which is to fit a straight line to the graph. And you can see there's quite a bit of scatter. But it's pretty obvious that there is some sort of connection going on there. Now, Hubble realized that one way that you can get a simple linear connection between the distance to an object and its velocity is if all the objects are embedded in a space that is expanding. And so Hubble was the first person to provide really strong evidence that our universe was expanding and getting bigger and bigger and bigger with time. And this graph was basically his evidence. Other people had predicted that this could be possible and it might be happening, but those were all theoretical arguments and not based on observations. So I'm going to pause here for a moment, and I'm going to ask people if they have questions to type their questions or let Mark unmute them. While people are asking questions, those of you with the paper and pencil and calculator can look at this graph and see if you can calculate the slope of the line, the rise over the run. So those of you with calculators, see if you can figure out the slope of this line in the Hubble diagram. And those of you with questions, fire away.
So I've unmuted everyone. You can feel free to ask a question if you have one. Got a couple people typing.
Typing, okay.
Tony says 450. Tim Haywood says 450.
Okay.
Bob Easterly says 4 divided by 9.
Maybe 400, 4,000 divided by 9.
Gary says 400 kilometers per second per megaparsec.
Kilometers per second per megaparsec. Why, yes, that is the unit. It's the vertical is kilometers per second, and the horizontal is megaparsecs. So you divide the slope, you get rise over run, kilometers per second per megaparsec. Exactly. And we're going to talk about those units in just a moment. I'm glad to see that people are coming up with numbers that are like 400 or 450 because that's what Hubble said. He said, yeah, I get this straight line and the slope is like 450 kilometers per second per megaparsec. So that was in 1929. Hubble first published this value for the Hubble constant, and it wasn't called the Hubble constant then, it was called something else. But in the years since, people have attached the name of the Hubble constant to it because Hubble. All right, so if you scroll down just a tad, there are some equations, 2 big equations, and let's look at those. So there we have it in black and white, as people have shown. The slope in this diagram was something like 450 or 500 kilometers per second per megaparsec. And so the Hubble constant, in the years since then, we've attached a capital H with a 0 subscript. And there's its value, roughly 500, maybe 450 is close enough. So, what did that mean? Well, it turns out that if you can measure this relationship between velocity and distance, you can figure out roughly the age of the universe. Here's how it works. If you scroll down a little more, please, you'll see a simple little table. Okay, suppose that you go to a race. There's like a cross-country race. People are going from Rochester to Los Angeles. And you get there just soon after it started. And you notice there are 3 cars shown on a display. There's a helicopter and planes, and they're measuring where the cars are and showing pictures. And 3 cars in particular are sort of spread out along the road as they're traveling. One of them is 60 miles away from the start line, and it's traveling at 30 miles an hour. Another one is 120 miles away, and it's going faster. And a third one is 180 miles away, and it is the fastest. Notice that there's a relationship between how far away the car is and how fast it's moving. Can anyone take the information in this table and figure out how long ago our race started?
Gary says it started 2 hours ago.
2 hours ago, yes. I wonder how he did that. How did he come up with 2 hours?
Peter
Well,
said 2 hours as well.
2 hours. If you simply scroll down a bit, if you simply take the distance of each car, you'll see that that distance is some combination of its speed times how long it's been driving. So if you want to figure out how long the car has been going, you just do a little algebra and divide the distance by the speed. So that seems pretty obvious. We can all do that, I think, pretty much in our heads with cars and miles an hour. Notice that in that equation, we've got distance on the top and speed on the bottom. But the way that we just defined the Hubble constant is the opposite. It's speed on the top and distance on the bottom. And that means that instead of having units of time, the Hubble constant must have units of 1/time. And that's true. If you notice that a system of objects is expanding and you measure the relationship between distance and speed, that tells you roughly how long the system has been expanding. In other words, it tells you roughly the age of the universe. All you have to do is take that h0 and turn it upside down. So if you would scroll down just a bit more, Mark, you'll see that that we have h0. Its units are a little bit of a problem. We've got kilometers per second on the top there, right? And we've got megaparsecs on the bottom. And supposedly this is going to come into something that's sort of like an age. So we expect to get units that are like seconds or maybe 1/seconds. But in order to make that work, we have to fiddle around with the units. So in that second line, I've gone through the conversion of turning megaparsecs into kilometers. And then I do the division because you have kilometers on the top and kilometers on the bottom. So the kilometers cancel out and you're left with a way of expressing the Hubble constant that most people do not do, but they could. You can say that the Hubble constant is some very small number of inverse seconds, which seems a little unusual, and it's hard to say things that are 10 to the minus 17. That's why we usually use kilometers per second per megaparsec, because you can understand what's going on. There's a speed and a distance. However, if you choose to express the Hubble constant in this funny way as 1/seconds, then it's very easy to get the age of the universe. You just do 1/the value of the Hubble constant. And if any of you at home have calculators, as I suggested you get out, then you could do 1/that number, and you could tell me a rough estimate of the age of the universe based upon the Hubble constant there. Does anyone want to tell me roughly how old the universe should be based upon this 500 kilometers per second per megaparsec?
I have a guess of 2 billion years.
A guess of 2 billion years. Wow, I wonder if that came from, did that come from Valerie?
It did not.
I was thinking that if there's anyone who can convert seconds to billions of years, it would be Valerie. Anyway, whoever that was, I can't see, congratulations. Because if you scroll down, you will see that indeed, if you do the reciprocal of h0 with that value, you get something like 6 times 10 to the 16 seconds, or about 2 billion years. So yes, congratulations. In 1929, Mr. Hubble and all those other scientists could say, well, based upon the measurements of the distance and velocities of galaxies, the universe should be about 2 billion years old. Now, could you zoom in just a bit more, Mark, please, so that the letters are bigger and easier to read? Great, thanks. So that's sort of good news, but it's also sort of bad news. And the reason it's only sort of good news is that other scientists in other fields like geology and physics, and even some other astronomers, they all had their own ways of measuring the ages of really old things. Like the geologists would figure out how old really old rocks were or how old meteorites were. And some astronomers figured out, based on the motions of stars and clusters, how old the clusters were. And the good news was that everyone was in the billions of years, so that's good. But the bad news was that the universe seemed to be younger than some of the things inside of it. So that's not good. And for about 10 or 15 years, this was a bit of a puzzle. The measurements of galaxies kept giving an age that was somewhat younger than the oldest rocks, which definitely not a good thing. So it wasn't until the 1950s and the 1960s that astronomers and other scientists figured out two keys to the puzzle. So there are two main big reasons why this Hubble constant age of the universe was not right. And that's because the Hubble constant itself was too big. And so for the rest of my talk, which is like the next 20 minutes or so, I'm going to try to talk about these two reasons that made the Hubble constant too big. I'll pause here for a moment because I need to pause. If people have questions, they can shout them out.
Everybody's unmuted. If you have a question, go ahead.
All right, well.
No questions.
Yeah, no questions. Let's move on. What I'm going to do is talk about two things. One of them involves populations of stars, and the other involves confusion. So let's start with stellar populations. If you'd scroll down just a tad to the next picture, you'll see a light curve. This is the light curve of a star that gets brighter and then fainter, and then brighter and then fainter, and then brighter and then fainter. It has sort of a very sharp rise and then a slow gradual decline in brightness. This is a Cepheid star, and I think most of you probably know that Cepheids are really excellent stars for astronomers because their luminosity is related to their period, and it's really easy to measure the period of a variable star. So we can easily determine the period and then figure out the luminosity, and that lets us use Cepheids to measure distances. So if you're into measuring distances, say distances to other galaxies, Cepheids are the right thing for you. This relationship between period and luminosity was measured first by an astronomer named Henrietta Leavitt, who is shown in the next picture. Let's all say hi to Henrietta. Scroll down, please. There she is. Hi, Henrietta. Henrietta Leavitt, hard at work. She used Cepheids in the Magellanic Clouds to find this relationship. And so she is the person who gave us a very important tool for measuring distances. So let me tell you how this works. If you scroll down to the next picture, you'll see a graph that shows period on the horizontal axis. So short periods are on the left and long periods are on the right. And then the absolute magnitude is on the y-axis. So faint things are near the bottom and bright things are near the top. And if you look at that graph, I think you'll agree there is a nice simple relationship. The longer the period, the brighter the star. And so astronomers, being scientists, scroll down please, they made a linear fit. And by golly, that linear fit looks pretty darn good if you choose your axes properly. And so astronomers said, hey, you give us a period, we will give you an absolute magnitude, and then from that, we can compare that to the apparent magnitude, and we'll get the distance to that star. And if that star is in a galaxy, then by golly, we'll know the distance to that galaxy. Okay, so far so good. Now here comes the tricky part. The Cepheids are one type of pulsing star. They get bigger and smaller, brighter and fainter. Turns out there's another type of a star called an RR Lyrae star, which is somewhat smaller, less massive, less bright, but it does pulse. And back in the 1930s and 40s, as far as astronomers could tell, these RR Lyrae stars, they had shorter periods than Cepheids, and they had fainter luminosities, but it looked like they were right on that same linear relationship. And so astronomers said, hey, we can use RR Lyrae. There's a lot of them nearby in the Milky Way. We'll measure distances within the Milky Way using these RR Lyrae stars. And then we'll measure distances to other galaxies using Cepheid stars. And because they're on the same linear relationship, everything will work out perfectly, and our distances will be consistent. And that was great, until it wasn't. And it wasn't great when astronomers, one astronomer in particular, go ahead and do that next picture. We can look at the picture while I'm talking. So in 1943, it was in the middle of World War II, and there was a German astronomer named Walter Baade who was working in California, in Pasadena. And because he was a German national, he wasn't allowed to do any wartime work, which meant that poor guy, he had to use the 100-inch telescope. No, sorry, yeah, 100-inch telescope at Mount Wilson, because all the real astronomers were off doing war stuff. And so in 1943, he had a whole lot of time on this big telescope, and in 1943, Los Angeles was blacked out so that enemy bombers wouldn't bomb it or something. That combination meant Walter Baade had lots of time on the world's biggest telescope and the dark skies of Los Angeles. And with that, he was able to make measurements of the Andromeda Galaxy and its companions. This picture here is one of the companions of the Andromeda Galaxy. And he, for the first time, was able to see stars. Can you zoom in a bit? Just make this a bit bigger, Mark. I know it may be hard to see, but if you zoom in and look close to the center, you'll see what looks sort of like a peppery, yeah, that's good, sort of a salt and pepper look around the center there. That salt and peppery look, maybe it's a bad reproduction, is actually the detection of a whole bunch of faint, not that close. That's the whole bunch of faint red stars. These are red sensitive plates. We should probably zoom back out, or else we're going to go crazy when we hit the next step. So Baade in 1943 was able for the first time to detect individual red stars in Andromeda and its companions. And he said, my gosh, we thought the brightest stars in these galaxies would be blue, because the brightest stars in the Milky Way are blue. They're the hot blue young stars like in Orion. But in Andromeda's central bulge and in these companions, which are elliptical galaxies, the brightest stars were red. Very strange, he thought. And this puzzled people for a few years until they figured it out. So if you scroll down, I will try to explain what's going on in the next figure, but it's kind of weird. Can you scroll down so we can see the horizontal and vertical labels there? Yeah, great. So what this is some of you know what this is. It's a Hertzsprung-Russell diagram showing stars, and on the horizontal axis is their spectral type. The hot blue ones are over on the left, and the cool red ones are on the right. And on the vertical axis is their brightness. The very luminous ones are at the top. The faint ones are at the bottom. There are two sets of stars indicated on this diagram. I know it may be hard to see. One of them is hatched lines, and I've overdrawn them with a red marker, highlighted them in red. The other stars are kind of solid black. So it turns out that what Baade and other people figured out was this, that there were actually two populations or two groups of stars in the universe. One of them was a group of young stars. Their location on this HR diagram is shown by the solid black stuff. So they're really blue and bright. That's the top left end of the diagram. They fill up the bright blue end over there. And there were a few of them that had used up all their fuel, or most of their fuel, and had turned into red giants, and they're over on the solid black line over on the right. So those are the young stars. And because they were young, they called them population 1, like they were only 1 year old. But there was another group of stars that were much older. Because they're older, they were called population 2, like they were 2-year-olds instead of 1-year-olds. So population 2 are the old stars. They're shown in red here. And the brightest of these are maybe a little brighter than the brightest blue stars there. They're all red giants. These old stars, the really bright ones, are on the red giant branch. And this sort of distinction between a young population and an old population was a completely new idea. But as people looked over the next 5 or 6 years in the 1940s and early 1950s, they found much more evidence that there were some galaxies that were mostly old stars and some galaxies that were mostly young stars. And there are even some galaxies that had a mixture, like our own. Okay, what has this got to do with distances? If we scroll down quite a bit, so scroll to the next, yeah, that one. So it turned out that in the late 1940s and early 1950s, people went back and they looked at the RR Lyraes more carefully, and they said, oh, we had the distances to those stars measured wrong. You know, actually, they're quite a bit fainter than we thought they were. And so those two little blue squares in the lower left-hand diagram here, the RR Lyrae pulsing stars, they belonged to population 2. They were an old stellar population. The Cepheids belonged to population 1, the young guys. And it turns out that the properties of pulsing stars aren't the same for the old guys and the young guys. And so this beautiful relationship that held for all pulsing variables, it didn't hold anymore. On top of that, if you scroll down to the next one, some astronomers did some more digging and they found pulsing stars in old clusters, in globular clusters. They looked a lot like Cepheids. People call them type 2 Cepheids. But they were also, like the RR Lyraes, a member of the old stellar population, and they were also fainter than regular Cepheids. So there's this period luminosity diagram, but it's not the same for old stars and young stars. And it turns out that astronomers figured out, oh no, the old stars that we've been using to tie down our distances here in the Milky Way, those old stars are fainter than we thought, which means that the young Cepheids are brighter than we thought. And that means that if these stars in other galaxies called Cepheids that we're using to measure distances, if they're brighter than they thought they were, then those galaxies are farther away than we thought they were. Whew, sorry, that was a lot to say. But anyway, if you scroll down to the next equation, please, Mark. The bottom line was, yeah, that equation right there. If the distances to all these galaxies were now bigger because the Cepheids are brighter than we thought, what does that do to the Hubble constant? In fact, the distances, just due to this stellar population business, seemed to increase by a factor of 2. If you take a number and you make its bottom get bigger by a factor of 2, that makes the number get smaller by a factor of 2. And so the Hubble constant in the early 1950s shrank down, boom, from about 500 to about 250, just because of this stellar population business. Whew. All right, I'm going to pause there and ask if people have any questions.
So I unmuted people. I think I unmuted people. Any questions? Dave Bishop asks, metal rich, metal poor Cepheids? Hold on, you got to unmute yourself, Dr. Richmond.
All right. Okay.
There you go.
So it turns out that yes, the metallicity of the stellar populations is also different. So the younger stars tend to be more metal rich and the older stars tend to be more metal poor. And that is part of the reason that they don't obey the same period luminosity relationship. So metallicity is another part of the equation. I'm not mentioning that here because there's a lot to talk about as it is, but you're right.
An element heavier than helium.
Yes.
Any other questions?
Nope. Okay.
All right, if you could scroll down, you'll see a couple of equations. Just go to those equations if you would. Yeah, we'll skip that. Right there, those equations, yep. Okay, so key number one to the shrinking of the Hubble constant was this discovery that there are two populations of stars, old stars and young stars. Now let's talk about key number two, because remember that first key only made the Hubble constant shrink by a factor of 2, and these days we'll see it's even smaller than 250 kilometers per second per megaparsec. So what's the second key reason? So the second key reason is distances measured by Mr. Hubble. So Hubble often used stars as signposts. He figured out that a lot of, in very nearby galaxies where you could measure individual stars pretty clearly, he figured out that the brightest stars are about magnitude minus 6.5. That's shown up there in that first paragraph of text. So an absolute magnitude of about minus 6.5, very bright. He figured if he could measure the apparent magnitude of these very bright stars in distant galaxies, he could use a little math and compare the apparent magnitude and the absolute magnitude, and there's a way you can determine the distance to an object based upon that difference in magnitudes. And the two equations I have there are equations most astronomy students might recognize. If you know the apparent magnitude, that's little m, and you know the absolute magnitude, that's big M, you can figure out distance. Okay, so that was Hubble's main method for measuring distances back in the 1920s and 30s and 40s. So let's try it and see how well it works. So could you scroll down to this galaxy, please? I would like to know if anyone can recognize and identify that galaxy. It's a relatively big, relatively nearby, beautiful face-on spiral.
Go ahead, type it in if you know what it is, or say it out loud. I don't think everybody's muted at the moment.
M51?
M51, good guess. Not quite. There's no big companion at the end of one of the spiral arms.
True.
Somebody said the Pinwheel Galaxy, or M100.
M100 is another very good guess. Not quite. It turns out if you scroll down, it is M100. Oh, so close. And so in the 1920s and 30s, Hubble said, well, based upon my pictures of this galaxy, the brightest stars I can see in the galaxy are about magnitude 19. So if you take that absolute magnitude of minus 6.5 and apparent magnitude of 19 and you plug them into that formula, you get a distance of, I'll do the math myself, about 1.3 megaparsecs. So according to Hubble, this galaxy, which by the way is in the Virgo cluster, is at about 1.3 megaparsecs. So if you scroll down, you will see my attempt to show you the material Hubble was working with. So this is, I apologize, this is a photograph of a printed page in a book sitting next to me here in my house. This is called the Hubble Atlas of Galaxies, and it's a collection of reproductions, photographs that were used by people like Sandage and Hubble. They were taken by the Mount Wilson 100-inch and later the Palomar 200-inch telescope. And it's a reproduction of a print of a reproduction, so it's not as good as the original by any means. But this is sort of what Hubble was doing. He was taking a magnifying glass, looking at pictures like this and trying to identify the brightest stars. It's not so easy. You can sort of see that well, you can definitely see the spiral arms, right? And you can see some big bright stars. So the big bright things, Mark just point, yeah, those are stars in our own Milky Way that just happen to be in that area, in that range, in that direction on the sky. The stars in the galaxy itself are way, way smaller and tinier and fainter. So it's a hard thing to look at a picture like that and say, aha, there's a star, and then it's even harder to measure its magnitude accurately. Now these days, if you scroll down, you'll see a modern picture of the same galaxy where it might be a little bit easier to make out individual stars. So what I'm going to do is we're going to take a trip zooming in to that gold box. So the next picture is zooms in there. Oh, now we can see more stars in galaxies. What I'm going to do is zoom in even further. So one more scroll down, please. So here we have, great. And can you zoom out just a tad so we can see a little bit more? This is an HST picture of M100, or rather an HST picture of one small section of it. And if we just let it sit there on the screen for a moment, we'll see the resolution of the screen improve. Can you make out individual stars in a picture like this? I would say that the answer is yes. So what I'm going to do is I'm going to pick out what I think are 5 objects, and I'm going to give you guys a quiz on those 5 objects. So if you'd scroll down just a bit, please, to the next picture where I've circled some things. Yep. Yeah, if you can just zoom out one more time, Mark. Oh, there we go. So you can see them all. 1, 2, 3, 4, 5. See, I've got A, B, C, D, E, F. I guess that's 6 objects. Okay. Ignore object F. Object F is bizarre. I'll talk about it later if you ask me questions. A, B, C, D, and E. How many of those are stars? And how many of A, B, C, D, E are not stars? That is the question. So make up your mind here. Yeah, you can jot them down if you want to.
Somebody says 0 are stars.
Oh my, 0 are stars. Bold move there, yes.
I think that there's 3 stars there.
Huh. If you zoom out once more, I think we'll get a side-by-side comparison. There's a picture that's just below it on your screen. Oh no, don't scroll. Just scroll down. Just scroll down. Yeah. There we go. So here, right and left, the black and white one on the right, the color one on the left, that's a side-by-side showing the Hubble Space Telescope picture on the left, and the photograph taken back in the 1940s on the right.
Oh my goodness.
And you can see I've identified A, D, and E in both pictures. You can see that things are a little bit more clear in the recent photograph, right?
No doubt.
So Hubble, back in the 1920s and 30s, he's looking at things like you see on the right and saying, is that a star or not? You can see why it wasn't such an easy job. Okay, so can you scroll down one more time, Mark, so we can get a nice clear picture of HST with the labels? Yeah, that's good. So in this picture, I think that items A, B, and C are all stars. A and B are kind of bluish, and C is kind of reddish. I think that objects D and E, object D is I think it's probably 2 clusters of stars sort of close together and overlapping, and object E is definitely a big cluster of stars right in one of the spiral arms. So these days, with pictures like this, it's pretty easy to pick out and measure the properties of individual stars in another galaxy because we have such good instruments, both telescopes and cameras. I used a simple tool. If you like looking at pictures like this and trying to measure them, there's a website called the Hubble Legacy Archive that lets you look through all the pictures Hubble's taken and then lets you interactively point at things in the pictures, and it will tell you how bright they are in magnitudes. Really fun. And I use that tool to show the table that is down below. So just scroll down to the table, please. Yep, there we go. So look at those numbers. The number you should concentrate on is the one in the column marked F555W. That's the magnitude, apparent magnitude in the V band, approximately. And the 3 objects that I think are stars are the first 3. The average sort of value for how bright is the brightest star is something like magnitude 23 or maybe 22.5. And if you scroll down just a tad, Mark, you'll see a graph there. That graph, yeah, that one. That graph is a color magnitude diagram made by real astronomers, Wendy Friedman and others, who were using the Hubble Space Telescope to look at this galaxy. And they measured much more carefully than I did how bright the stars are. And you can see that the brightest stars that they measured are about magnitude 23 or maybe 22.5, exactly. Now remember, when Hubble was doing this, Hubble said the brightest stars in this galaxy are magnitude 19. That's because he was mixing up clusters of stars and sometimes H2 regions with, well, he thought they were individual stars. They were really clusters of 10 or 100 or 50 or 28 stars. And that's why they weren't the right magnitude. He overestimated the magnitudes, and that meant that when he calculated the distances, he got them wrong. If you'll scroll down just a tad, you will see a little calculation which says that if you're off in magnitudes by about 3 magnitudes, could you make the text a little bit bigger, please, Mark? If you'll see that if you make an error in 3 magnitudes in brightness, that corresponds to an error of a factor of 2 in distance. And so, because of this mistake of identifying what were really clusters of stars as individual stars, Hubble's estimates of distance were off by another factor of 2. And so that graph that you can see there with the red and blue points, yeah. So there is the Hubble diagram that I showed you at the beginning of today with velocity on the vertical axis and distance on the horizontal. Hubble's original measurements are shown in red from 1929. A more recent calculation, measurement of distances are shown in blue. You can see the velocities are about the same, but the distances have gotten way bigger, way bigger. And that means the Hubble constant has gotten way smaller. Okay, with this mention of the second of the 2 big differences, I'll pause and take questions.
So everybody's unmuted. Feel free to ask a question. If you're trying to ask a question and you're not unmuted, let me know. Text me or chat.
Okay. Well, it's almost over. I know this has gone on a long time. I'm about to bring this to an end here. So there were several reasons why the original estimates for distance were wrong. They were too small back then. They're much bigger now, the distances. And that means the Hubble constant's value has shrunk by almost a factor of 10. Okay. So in this last little bit, I'm just going to bring you up to date with where things stand today. So in the 1970s and 80s, this graph here shows published estimates of the Hubble constant on the y-axis and time, years when it was published on the x-axis. So history is going to the right here. And you can see that in the 1980s and 90s, there seemed to be 2 different values for the Hubble constant, depending on whom you asked. If you asked a group of American astronomers led by a guy named Alan Sandage, he'd say, oh, it's around 50 or 60. If you asked a group of European astronomers led by Gerard de Globular, he'd say, oh, no, it's more like 90 or 100. So there was this awkward period of a couple of decades when we thought we knew the value of the Hubble constant, but it was a difference of a factor of 2, which is not a good thing. In more recent years, as people have gotten better instruments in different wavelength ranges, like HST and the optical, but a bunch of X-ray and radio telescopes as well, those different estimates have started to converge, and you can see that people are starting to agree on a value when you get to like the 2000s and 2010. And if you scroll down once more, you'll see an even more recent zoom in. So here we are just since the year 2000. And, yep, and here we are. You can see that in the last 10 years, there are still two groups based using two different methods. But instead of differing by a factor of 2, now they only differ by 3 or 4 kilometers per second per megaparsec. So the good news is that we used to disagree by 50 kilometers per second per megaparsec, and now we only disagree by 3. That's the good news. The bad news is, as you can see by looking at the error bars, that the error bars of these two different methods do not overlap. And so, one of the biggest questions in astronomy today is, how come people using two different methods of measuring the Hubble constant get two different values that don't agree? I could talk about those, but we've been going on pretty long, so I won't. I'll leave time in questions if people want to ask. But if you would do me a favor, Mark, if you scroll down, I want to tell you how bad this disagreement is. You might think that a difference of 3 or 4 kilometers a second is nothing. Can you scroll down a little further, please? There's a picture. Yeah, that picture. There's a wonderful place called the Astrophysics Data System. It is a catalog, an archive of all the papers published in astronomy ever. It's wonderful. You can search through it. If you go to this website and you say, I'm interested in papers using the term, and if you look down near the bottom, can you point with your cursor to the term that says Hubble tension? Yeah. That's what they call it these days. The difference between the big value and the small value, the Hubble tension. Just in the last year, if you click, Mark, on this if you click on the picture, just click your mouse there, it will perform a search for you going to the Astrophysics Data Service. How many papers are there with the word Hubble tension published in just the last year? Can you scroll up to the top? It'll tell you a list of how many papers there are just in 1 year.
187 results.
So the word Hubble tension, it's a hot topic. I'm not kidding. Hundreds of papers each year trying to explain, how come these guys get this value? How come these other guys get that value? It is one of the biggest puzzles today, even though it's only 3 kilometers per second per megaparsec. So with that curious note, if you could hit the back button on your browser, please, Mark, to take us back to the webpage. I will end my talk and ask for questions. Down at the bottom, you can see there are more references. If you're interested, there's other places you can read. And I'll mention there at the end, the last item, I taught a whole course on this business of measuring distances and figuring out the Hubble constant. And so if you're really interested in the topic, I urge you to go click on that link and read through some of the material. So thanks very much, and I'll take your questions.
Okay, have everybody unmuted? I have a question. It says, what do the two differing Hubble values mean in terms of difference in resulting age of the universe?
Oh, the difference in the ages is very small. It's probably just about 1 billion years or so, something like 12.5 billion years versus 13.5 billion years. And actually, the bigger uncertainty in the age of the universe these days is, what is the value of the cosmological constant? What is the amount of dark matter in the universe? Not so much what is the value of the Hubble constant. In other words, what's really confusing us now or keeping us from knowing the answer is not so much how fast is the universe expanding. We've got that down pretty well. What's giving us trouble nowadays is, well, just what the heck is the universe made out of? And how much matter is there to exert gravitational forces and slow things down? Other questions?
Somebody commented it was the cover story of the Scientific American this past month.
It's the thing that astronomers are focused on, I guess. It's this and exoplanets are the two big things, I think.
I have a question of the two divergent groups today. Which do you think is more likely to be right, and why?
Oh, I am solidly in the camp of the slightly larger value. That's based on local measurements where people actually measure distances to galaxies. And I am in favor of it not for any good scientific reasons, but it's the team I play on, so I'm rooting hard for them.
We got someone else typing in a question here, I think. No, maybe not. Oh, I have some thank yous. So good lecture.
Oh, well, I'm sorry about the technical difficulties. Please do feel free to browse through all these materials as you wish. And if you have questions later on after you've been reading them, please send me an email and I'll do my best to answer. And Mark, you'll send out a URL to people so they know where to go?
Yes. Yes.
Thank you very much.
It'll be on this. I'll put it with my, I'll put the URL on my notes when I give it to, Peter to hook up.
Great. Thanks very much. Okay,
All
back
right.
to you.
All right. One more question for you, Michael. Is it okay to share the lecture notes with friends?
The materials are on a public web server. I put them there so people can use them.
Okay. I have claps and applause over here, and many thanks. So thank you, Dr. Richmond. Appreciate this, and we actually we're able to pull this off. So thank you very much. Anybody have questions for me? Awesome. Well, thanks everyone. You're unmuted. If you want to talk a little bit, you're free to do so. And then I'm gonna close the meeting down after if there's nothing else going on. Clear skies. Thank you. Thanks everyone. All right. I can't invite you to all the Applebee's afterwards, but I can certainly invite you to stop in your refrigerator, grab yourself a beverage or a snack. Thanks for coming, everyone. Oh, I have updates from maybe our remote members, Valerie or Rick or Andy. Anybody want to give us an idea how they're doing? How's things in Thailand, Andy? I don't know if Andy's got audio on or not. Andy says he hasn't done any observing in a while. Is it rainy season? No, just busy. Valerie says thumbs up for me. She's surviving. Hard to do any outreach when you're locked up, or like we all are. Who else? Rick, are you still around? You had some nice pictures from Georgia of the of Venus floating through the Pleiades last night. I don't know if Rick's got his audio on or not. I'll put my video back on since we're not worried about bandwidth at this point. Well, this is a cool way to get together, and what we'll probably do is if we can't meet in May, we'll do this again. We'll talk with I forgot our professor, the doing the gravitational waves. See if we can't do this again then. Of course, it does limit my talking, which is fine by me. If we're not having any events or anything, at least we can get together this way. So Bill Rogers mentions that we're trying to move to paperless renewals for this period. All right. With that, it's nice to see some of the smiling faces up there. Some people look some people look really comfortable. How many people have slippers on? Raise your hands if I could see you and you have slippers on. Ah, there we go. I got at least 3.
How many are wearing pants?
Oh, no.
Yeah, I wasn't going to ask that, but you did. BJ's all the way, says Valerie. And Dr. Richmond was wearing slippers too, so that was a comfortable talk.
Thanks, Mark. Great
So
job.
well, I'm glad we're able to do it. So thank you for thanking me, but I'm glad we were able to do it. It's a fun thing to do, and it's nice to have this alternative to use. And we really weren't
thanks,
that
Mark.
many. I think at peak we were somewhere in the mid 60s of users. I was afraid that we might be well over 100, but we were able to see a lot of people that we don't normally see. So thanks to everybody who came. All right, I'm going to stop the recording. Yeah.
Yeah, Mark, it was very helpful to me that you sent a link for the